Alright, so for this Lab 5, I chose to do a slinky. Alright. I did the slinky. So first we have Newton's second law, the momentum principle, which states a system's change of momentum is proportional to a net force. And then we have the gravitational force, which is a constant 9.8 meters per second squared. And then you have the drag force, which is non-constant and is equal to the proportionality constant times the current velocity squared. We're going to use two things mainly position velocity update formulas. And then the initial conditions of the mass of the slinky are 22 kilograms. And obviously the initial y velocity is going to be 0. The purpose of this lab is to use skills and resources that we gained and used so far in the course, and we're going to apply them to the problem we designed. And then we're basically going to show mastery over those prior topics to show what we actually learned. A brief overview: observe the motion of the falling slinky and track its position with the software. Then create a computational model of the scenario using Python. Compare the results, and brief overview of the final result is that the bottom of the slinky is going to remain stationary until the top hits it. For the experimental part, basically the slinky is the slinky, and the Earth's surroundings is the air. The system is the slinky, and the Earth's surroundings is the air. The mass is 0.22 kilograms. The initial velocity is 0. The initial stretch length is 1.22 meters after acceleration. And basically, you just track the position as it falls, and you can see that it doesn't move until it gets hit. Then the computational model plugged in the initial conditions I mentioned before and used Newton's second law to find force, which is the sum of the force of gravity and the tension force of the slinky when it's in static equilibrium, and then the net force equals the force of gravity and the force of drag when the slinky is falling. And then I use the velocity update formula in both time steps and calculate the object's new velocity. And then I use that to find the new position using the position update formula. And then I printed out the time and y position of the slinky to use that data for the graph. And then this is my combined model. What's going on in the video is that the top of the slinky begins falling and the bottom does not. However, if you track the center of mass, the slinky begins falling and the bottom does not. However, if you track the center of mass of the slinky, you'll know that falling at a constant rate because there's a spring force acting on both sides of the slinky. On the bottom, spring force is up, and at the top, it's down. And then due to gravity, there's an initial downward force, which means the bottom of the slinky has a net force of 0, and the top has a greater net force. The two models follow each other very well, just with some slight discrepancies towards the end, which could be human error. What does it mean? Basically, as said before, the forces in the y direction cancel out, although we do have a gravitational force acting downwards as the slinky acts as a big spring and counteracts the force of tension that is equal and opposite. So obviously the bottom end is going to have a net force of 0, therefore it remains stationary. Some sources of external forces some sources of error are external forces and human error. The external forces not accounted for would be the wind resistance. And the human error would be that we're just dropping it. So there could be some error with how we let go. We talked about Newton's second law, gravitational drag force, and notice how the bottom of the slinky would remain stationary because the net force is 0.